Yeah, good afternoon, every one of you. So we were seeing this until the last class, Unit 1, Nuclear Materials, Explosives and Propellants. So to some extent, we have covered this Unit 1. So today we are going to see this uranium and nuclear fuel cycles, and then major important components and uranium conversion processes. And finally, the role of chemical engineering in nuclear engineering. So first we know that what are the nuclear materials. So according to IEEA classifications, nuclear materials are one of the nuclear material is uranium. So largely the uranium or thorium will be used to produce the nuclear power. So to produce that nuclear power from uranium or thorium, there are many fuel grade metals are there that we have to categorize into two types. One is a fission fuel, another one is a fertile fuel. So what is the meaning of this fission fuel and fertile fuel is, so the fuel which can directly be used in the nuclear reactor to generate electricity or power, so is called as fission fuel. But whereas fertile fuel we cannot use directly. Okay, we cannot use directly them into the nuclear reactor. Okay, we have to, that fuels has to undergo certain conversion processes before it can be sent to the fission reactors. So there are two types of fuels. One is a fission fuel, another one is a fertile fuel. Usually the fission fuels, they are the elements or compounds such as oxides, carbides, nitrides, or sulfates or chlorides of uranium. So the best example for this one is U-233 and U-235. Okay, U-233 and U-235 is the examples of fission fuel, which we can directly use them into the reactors, nuclear power reactors. But the next category of fuels are the fertile fuels. Okay, they are the atomic elements. Okay, usually these fertile fuels are the atomic elements which thereby undergo in nuclear reactions gives a fission fuel. So after undergoing certain reaction only they will give a fission fuel. Then these fuels will be maybe included as U-238 we can say. Then another is thorium-232 is also one type of fertile fuel. These fuels cannot be used directly into the fission reactors. Only fissionable fuels or fission fuels can only be used in the fission reactors. But the fertile fuels has to undergo certain transformation before it goes directly production to the nuclear in the nuclear power plant. So uranium. First we will see generally what is uranium. So uranium is a very basic material, or it's a common material to produce power from the nuclear power plants. Then various isotopic forms of uranium are available like U-230, U-233, U-235, 238, 239. Okay, there are many forms are there, neptunium, plutonium, all this will be there. Various isotopic forms will be involved. Then atomic number. So usually this atomic number will be 92, which means there are 92 protons, and similarly there are 92 electrons. So what is this U-233? Okay, just I will explain that one. What is this U-233? So generally see, the uranium metal will be represented using U. Okay, this will be represented using U. So what is this 230? We can say 235, for example, you take. So here this is 92. What is the meaning of this 92? This 92 is nothing but your atomic number. So uranium atomic number is 92. At the same time, this is also equal to number of protons, and at the same time this is also equal to number of electrons. Then what is this 235? So 235, as in the introduction class I have told you, this is nothing but mass number. So protons and neutrons, okay, protons and neutrons will have today when there is a nucleus. Okay, when there is a nucleus there will be protons, neutrons, then on top of this nucleus, okay, together this one protons and neutrons is called as a nucleus. On around this nucleus there will be some revolving electron cloud, so electrons will be there. Together all this one we will call we are calling this as a atom. We are calling this as a atom. So number of protons and number of neutrons. So what is neutron? Neutron is nothing but neutral charge, no charge. Then proton is a positive charge, electron is a negative charge. So what is mass number? So how to determine the neutrons using the mass number and this atomic number? So that will be number of neutrons, especially for this element. So number of neutrons is equal to this mass number 235 minus 92. So how much you are getting? That thing is the number of neutrons which are present in this particular element. So that is the meaning of this one. So for example, this is U92, U238. Okay, similarly, this is a atomic number, this is a mass number, and when you subtract this mass number with atomic number, you will get a number of neutrons. So usually that will be represented like that. So that is the meaning of this fuels. So usually this fission fuels are U233 and U235, or the directly we can use them into the fission reactor. But whereas fertile fuel has to undergo certain reactions, then only they will be converted to the fission fuels and we can use to produce power from that particular fuel. Okay, then if you see, there are very small fraction of fission fuels are available on Earth. Okay, where whatever the soil is there, very small fraction. Okay, much of the fuel, much of the uranium is available as a fertile fuel. Okay, nearly 99% metal, whatever we find on this earth is fertile fuel only. Okay, very small, minute amount of fuel, which is fissionable fuel, is available in on our earth. Then atomic number is 92, which means also the electron number. And usually the uranium will be in a silvery gray metal in actinide series. So in the periodic table, if you see in the actinide series, this is located. So this will be somewhat silvery gray metal. And its density usually 70% higher than the lead. Okay, compared to lead, it is 70% higher. And this is somewhat slightly lower density compared to the gold or tungsten. They are also metal. So compared to this one, this is slightly lower density compared to that gold and tungsten. Then usually they are found in very low concentrations, usually beach sands, monazite sand, okay, pitch blende, cottonite, phosphate rock inclusions. In that one, very small amount this uranium will be present and extracted from ore like uranite. In the uranite, that is called as a uranite, usually the uranium will be extracted from this ore. Then all naturally found uranium contains only 0.714%, means divided by 100. That much fraction only found as a fission fuel, and rest all the fuel, whatever the fuel find out is, that is a fertile fuel, U238 grade fertile fuel. So enrichment must be done by gaseous diffusion using UF6. So enrichment has to be done by using this uranium hexafluoride. So these are the facts, various facts of uranium. Then what are the sources of this uranium? Like I already said you, the sands, various sands, beach sands, monazite sands, are the various sources from where uranium can be extracted. So first one is a pitch blende. So usually in the pitch blends, the percentage of uranium in this pitch blend will be around 1 to greater than 10% uranium will be there. And whereas in carnotite, in the carnotite ore, the uranium will be 0.1 to 0.5% uranium will be there. And in the monazite sand, only 0.2% uranium will be there. And in the phosphate rock inclusions, this type of looking, so that will be 0.01 to 0.03% will be there. So from this fraction, okay, from this type of ores, we have to collect this fraction of uranium and can be used in our nuclear fuel generation. So this is about uranium. Okay, some of the facts, some of the sources where we can find out the uranium sources. Then after obtaining the uranium sources, all these sources, after obtaining uranium, so uranium will be present in very small amount. So that amount needs to be first they have to undergo mining process. They have to mine that one, like a coal mining you might have seen. Okay, Singareni, Colarise, whatever they are there. So from that, whatever the coal they are obtaining, no, like sand blasting or this limestone blasting. Okay, there you can find the mining. Okay, after mining that particular ore, it will be extracted. It will be subjected to extraction operation and then concentrated because of very minute, very low amount of uranium will be presented in that particular sand composition. Then after concentration, it will be sent. If the uranium, whatever the uranium find here is a fertile fuel, a fission fuel, so that will be directly sent to the reactor 1. Okay, reactor which is labeled as reactor 1. So this reactor is nothing but converter power reactor, okay, which will only operate using the fission fuel. If your after concentrating your uranium ore, if these are the fission fuels, then that will be sent to the reactor 1 to generate an power. Okay, if there are fertile fuels, then it will be sent to the enrichment by gases using UF6. Okay, uranium hexafluoride will be used to enrich by gases diffusion, means sorting out of the fuel. Okay, if in the sorting out of fuel, so fertile fuels will be separated from the fission fuel. If the fission fuel like U235 is found out, it will be once again sent to the reactor 1, which is called as a converter power reactor, which will only operate using the fission fuel. Then the fertile fuels, nothing but U238, that fuel will be sent to the this reactor, which is a breeder power reactor, or which can produce excess fission fuels, mean it can operate on the fertile fuels. Okay, U238 fertile fuel will be sent to this one. If there is a U235, which is a fission fuel, will be sent to this one. Okay, we'll send it to reactor 1. If that is a fertile fuel, it has to be sent to the reactor number 2, where once again it has to undergo many processes inside, then only it can generate a power which is in excess of the fission fuel. Then after fuel generation, there will be many spent fuel will be there. Okay, spent fuel, spent uranium products will be there. That will be sent to the uranium spent fuel reprocessing plant. From there, fission products will be separated. So useful fission products, like what we say, many isotopes of this iodine. Okay, iodine. Then we can say this one, cesium, strontium, xenon, barium. All these are the fission products. Okay, various isotopes of iodine, cesium, strontium, xenon, barium can be found out in the fission products. Then it will be separated out. Okay, useful products will be taken on one side, whereas radioactive decay metals, okay, decay materials, whatever the radioactive metals are there, that will be safely sent to the disposal unit. Then similarly in the breeder unit also, reactor number 2 also, same thing. After extracting a fuel from this one, so whatever the spent fuel which is coming, so that will be sent to once again to the breeder blanket reprocessing unit. From there, whatever the fuels are there, which can be used further, which will be recycled back. And next part of the flow sheet is this one, thorium. So thorium is also one type of nuclear material which are abundantly available, especially in our India. Okay, thorium. So thorium also same, it has to undergo a similar process like ore mining, thorium ore mining, then extraction, concentration of that ore. Why? Because they will find out, they will found in very minute quantities on the earth. Then after concentration, it will be sent to the fuel fabrication. Because thorium 232 is also an fertile fuel, it has to go to the reactor 2. If it is a fission fuel, it has to go to the reactor 1. Okay, because the thorium is not a fission fuel, that's why it is once again going to the reactor number 2, which is a breeder reactor, breeder power reactor. From there, many series of processes will be undergone, and the fuel, the power will be produced from this unit. So this is the nuclear reactor fuel cycle. Okay, any doubts in this one?
No, sir.
Yeah, how the fuel will be produced. In the last class, we have seen the reaction, okay, nuclear fuel reaction, how the fuel will be produced. So same continuation of this topic only. Okay, fuels are there. We know this one. Fuels are two types of fuel. One is fertile, another one is fission fuel. So fission fuel is nothing but direct fuel, and these are indirect fuels. Okay, it has to undergo certain transformation process before it can be used as a fission fuel. So we have to see the fission reaction first. So what is the fission reaction? For example, you are taking this one. Okay, fertile fuel we will take. For example, first we will see the what is fertile fuel. So fertile fuel can be converted to fission fuel. How that fertile fuel can be converted to fission fuel, we will see here. Fertile to fission conversion. Okay, this will takes place as follows. For example, U92 238 is a, I think, fission fuel. This is fertile fuel. This is okay. Yeah, U238 is a fertile fuel. This fertile fuel has to be converted to fission fuel. How to convert that one? We have to supply one neutron there. Then this neutron will transform this uranium into other isotopic form, which is U92. This atomic number will not change, but we are supplying one neutron, thus will be addition to this uranium mass number, which is 239. Then this has to undergo one other transformation process. In each step, it will be releasing one electron anti-neutrino. Okay, in each step, whenever it is one isotopic form is converting to other isotopic form, it has to release one electron anti-neutrino. Means it's a very high energy electron, it will be released here. The next step is one more, it will be undergo a transformation, which is to neptunium, Np. Neptunium 93, which is whose atomic number is 93, and the mass number will be same because we are not adding any neutron here. So 239, it will be undergoing a transformation to neptunium. Then next, it will be coming to the plutonium, Pu 94, and we are not adding anything neutron here. So this is 239. So this is also a fission fuel. Fission fuel. Here also the next transformation, this is also releasing one electron anti-neutrino, which will be denoted by beta minus, beta to the power of minus. What is this one? This is electron anti-neutrino. This is called electron anti-neutrino. So all the fertile fuels has to undergo this type of transformation, and this has to form a fission fuel. Okay, then how the fission fuel will be undergoing the fission reaction? So for example, the fission fuel is this one, U23592. I think U235 is a fission fuel. Yeah, U235 is a directly fission fuel. We can directly use this here. So we have to supply one neutron. So this is a neutron. So this is a uranium in fission form. Okay, this is very important. Fissionable uranium form, this one. When you supply one neutron to this one, so it will be converted into two products, Xa plus Ya. Yesterday we have seen that one uranium product will be converted to two small molecules by the fission reaction. That is one thing I remember, barium, okay, Ba 144, then krypton Kr89. So this is that X is Ba 144 and this Y is Kr89, along with the liberation of 2 to 3 neutrons. Okay, 2 to 3 neutrons will also be released whenever the fission reaction is happening. So this 2 to 3 neutrons, whatever released, no, that will once again utilize the same reaction. So first we have to initiate by supplying one neutron. Next, it will take this neutron, whatever the generated neutron in the first cycle, it will be taking once again that neutron, and the same cycle will continue once again. So this is called as a chain reaction, because in every cycle there is a generation of 2 to 3 neutrons in every cycle. Because of this reason, this nuclear reactions will be very bombarding and very high energy, as well as very chain reaction, long chain reactions. So once they are initiated, it is very difficult to stop them because of their chain reactions. So this is the fertile fuel and fission fuel conversions, the meaning of various mass number, atomic number, different isotopes and everything, this one. Okay, I hope you understood this one.
Yes, sir.
Okay, then next one is topic. Yeah, this one flow sheet. This they are many times they are asking, explain in detail or draw a neat diagram of nuclear fuel reactor cycle or nuclear fuel cycle. They are asking. So you have to draw this one, and whatever the explanation I have given, that explanation you give. So before you have to explain what is uranium. So some of the facts of the uranium is given here, their sources, These sources they are asking many times in short answer questions. Sources. Then after drawing this one, so now we will concentrate more on this reactors. Okay, what is required to operate this reactor? This is a general flow sheet. Okay, after drawing a general flow sheet, there are other important question is also there, which is explain in detail about the major components or major important components of nuclear fission reactor. So fission reactor is this one. So in the nuclear fission reactor, what are the various components will be there? We will be discussing in detail about that one. So what are how this reactor will be operated? The first one is by fission fuel. It will be operated. So fuel needs to be there inside. Okay, there are two types of fuel in that one. Okay, this one. Okay, there are two types of fuel to operate that reactor. One is a fission fuel, another one is a fertile fuel. We know that one fission fuel is nothing but directly we can use into the nuclear reactor. That is called as a fission fuel. So U-233, U-235 and plutonium-239 are the fission fuels. And fertile fuels are U-238 and thorium U-230, thorium TH-232 is the fertile fuel. So the transformation of fertile fuel to the fission fuel can be happening using this reaction. Whatever I have drawn in the OneNote, the same thing here given this slide. Then next one is a structural component. So construction material of this particular reactor. So what type of construction material we have to use? That forms a structural component of this reactor. So what type of structural component it is? So the reactor structural components involve the material like with lower absorption, okay, lower absorption of neutron. So here if you see in the nuclear reaction, so in this reaction, there are 2 to 3 neutrons are forming in every cycle of nuclear reaction. So if the reactor construction material is neutron absorption capacity is there for that one. So what happens? These neutrons are unnecessarily wasted by absorbing into the reactor material. So in order to not to waste that neutrons, okay, only to use during the reaction, so we have to employ a low absorption of neutron, the material which absorbs very low neutrons. We have to choose as a construction material, like that materials are zirconia, alumina and stainless steel are usually employed to construct a reactor, fission reactor. So why we have to choose this only metals as a construction material? In order to not to absorb due to their low absorption capacity of neutrons, we will employ this type of metals, zirconia, alumina and stainless steel. The next major component is this. Okay, this reaction is very bombarding reaction, means it's a heat of energy. Okay, delta H is very high, 18 million kilowatt hour per kg of uranium, means it's a very high energy giving reaction. So that much energy giving reaction, if they are not controlled, okay, they will be having a serious accidental consequences. So we have to use the next structure, next component is a coolants. We have to cool the reactor every time, otherwise the reactor will be blasted. So after the nuclear reaction, huge amount of energy will be released. So the coolant like sodium, okay, like sodium, potassium alloy, bismuth, Bi, this one bismuth, and purified water we can use, and deuterium oxide we can use, okay, in order to cool the particular reaction inside the reactor. So then next one is the moderators. Why do we want this moderators? So the moderators are the materials required if the absorption of neutrons is to take place at or near the environmental temperature of the reactor. Means if you see in the reactor at these environmental conditions, whatever the reactor temperature is there, at that conditions, if the neutrons are wasting or neutrons are getting absorbed inside this material, so what happens? We have to use some moderators. What are these moderators? The fission neutrons liberated are of very extremely high energy. The whatever the neutrons released, 2 to 3 neutrons, that will be of very high energy and must be moderated to environmental temperature by non-absorption type collision. So it has to undergo a collision between moderator and that particular neutrons. Okay, with a moderating materials like pure graphite is one type of moderating material, Then next one is deuterium oxide is one type of moderating material, and water is also a moderating material. So this DTO, this is called as a heavy water. Deuterium oxide is called as a heavy water. This water is a normal water. Then this is a beryllium Be is forms as a moderator. Okay, there are four major important components in a nuclear fuel reactor. So that are, first one is a fuel. There are two types of fuel. One is a fission fuel, another one is a fertile fuel. Whenever fission fuels are there, we can use directly into the fission reactor, whereas fertile fuels has to undergo certain transformations before they can be used in the fission reactor. Then next is a structural component. So in order to lower the neutron absorption capacity, so we have to construct our reactor material in such a way that they should be having a very low neutron absorption capacity. The materials like zirconia, alumina and stainless steel can be used as a structural construction material of that reactor. Then coolants, since the this nuclear reactions are very energetic reaction and they will be liberating extremely high energy. Due to this fact, we have to cool the reactor. We have to supply some coolants to the reactor. So like a jacketed reactor, something like that. Then in that one, the coolants such as sodium metal, sodium potassium alloy, bismuth, purified water or heavy water like DTO, which is deuterium oxide, can be used as a coolant. And if at the environmental conditions of the reactor, if there is a absorption, neutron absorption is there. So in order to moderate that neutron absorption material, we have to collide them with a moderators. The moderators like pure graphite, heavy water and water, beryllium can also be used as a moderator in the reactors. So the uranium, thorium, neptunium, plutonium will be looking like this. So these are all the fuels of nuclear materials, which will be used as a fuel inside the reactor, fission reactor. Is that okay? Any doubts until here? What happened? Nobody is responding.
No doubt, sir.
Okay, yeah. Then I hope everybody is not having any doubts. The next process is important process, which is next question. Okay, these are the three questions. So first one, see, explain in detail about the nuclear fuel cycle or nuclear fuel reactor cycle. So that is one question. Then you have to draw this flow sheet and you have to explain this one, uranium, sources of uranium. Then you have to explain each and every step, what is going on inside. So in the notebook, it is clearly written. Then next question is important components of nuclear fission reactor. Okay, then you have to explain all these four important components. Then next question is explain various forms of a uranium. Okay, what are the various forms of uranium? Okay, you have to draw this flow sheet and explain what are the various forms or explain about the uranium conversion processes. This type of questions they may be asking. So this is the third question. So this is in this one uranium conversion processes. First one is a denitration. Okay, uranium. I will show you in detail this one. Yeah. So, so uranium conversion processes. So as said, this uranium will be just found out as a small, very trace element in the sands or in some nitrite material in the form of uranyl nitrile hexahydrate. Okay, in the form of uranyl nitrile hexanitrate. So in this form, it will be found out. UO2, NO3 twice 6H2O. So this is called as a uranyl nitrate hexa 6. This one is there, no 6. This is called hexahydrate, uranyl nitrate hexahydrate. So this when this is in the form of uranium, so this ore we can use to denitrify. The first step in conversion is a denitration of this uranyl nitrate hexahydrate. So this is called denitration. So how to denitrate this one? So to denitrate this one, the following reaction has to takes place. So that is denitration reaction is this one. So UO2 NO3 twice 6H2O will undergo a denitration means, so this will be converted to uranyl nitrate UO2 OH NO3 plus with the liberation of 5 molecules of water plus nitric acid will be liberated. For each step in the denitration, one molecule of nitric acid will be released, and further this uranyl nitrate will undergo further denitration process. So UO2 OH NO3 will undergo denitration further by liberating one molecule of uranium trioxide UO3, uranium trioxide. This is called uranium trioxide. Then along with the liberation of one molecule of nitric acid, HNO3 is a nitric acid. Then after denitration, what happens? The end product will be this one, UO3. So this one will be the end product after denitration step. And whatever the NO nitrous oxide or nitrous dioxide will be formed or separated in the form of nitric acid HNO3. So this off products will be liberated off, whereas this UO2 will further undergo a transformation. So the next step in conversion of uranium is UO3 has to be converted to UO2. So how to convert that one? From UO3 to UO2, what is the reaction? The reduction reaction has to take place. So we know that oxidation means addition of oxygen. Reduction means removal of oxygen or addition of hydrogen. So we have to add hydrogen to the UO3. Then the product formed is UO2. So how this reaction will take place? So this one is first reaction, which is nitration, denitration, and second is reduction reaction. So how it will take place? UO3 will be converted to UO2 plus half O2. So this UO2 is nothing but uranium dioxide. Uranium dioxide. So after converting this UO2, we can further convert this UO2 to many different uranium products. So among them, the first one will be like this. So this one, hydrofluorination. Hydrofluorination. So how to do this hydrofluorination? We have to add hydrofluorine, HF. Okay, hydrogen fluoride we have to add, or hydrofluoric acid we can tell this HF means. So this hydrofluoric acid, whenever you add to the UO2, that will convert your uranium. Further, your uranium can be converted to uranium tetrafluoride. Uranium tetrafluoride can be obtained. So how this reaction will be looking like? So third one is hydrofluorination. So hydrofluorination will take place like this. UO2 is the raw material for this hydrofluorination, plus we are adding here hydrogen fluoride, so HF, or hydrofluoric acid we can say. So HF means hydrogen fluoride, or we can say hydrofluoric acid. So whenever you add this HF to the UO2, it will be converted to UF4. UF4 is nothing but uranium tetrafluoride. Uranium tetrafluoride along with the liberation of 2H2O molecules. Then after this one, this uranium dioxide can also be converted to uranium carbide. How we can convert this uranium oxide to uranium dioxide to uranium carbide? So to convert that one, we have to pass this using what we say carbide furnacing. We have to pass them into the carbide furnacing. So carbide furnacing, what is this? We have to pass through the carbon C. Okay, carbon C we have to pass. So the fourth reaction will be carbide furnacing. Carbide furnacing. So how it will be carried out? UO2 plus carbon. Okay, nearly the 4 carbons will be mixed with uranium dioxide. So then it will be converted to uranium carbide UC2 plus along with the liberation of carbon monoxide. So this UC2 is nothing but uranium carbide. So uranium carbide you can found out here. So UC2, which is uranium carbide, along with liberation of carbon monoxide will be off gas, as be liberated as a off gas. Then after this further, this uranium tetrafluoride can also be converted into next product, which is this one, what this reduction. Okay, it will further undergo a reduction reaction. Reduction reaction. So how this reduction reaction will take place? Using this alkali metals. Okay, reduction using alkali metals. What are the alkali metals? Like calcium is one alkali metal, magnesium is one alkali metal. So using these metals, UF4 will be undergoing a reduction reaction. So what is this reduction reaction? Fifth one is once again the reduction using alkali metals like Ca, calcium or magnesium. So what is this reduction using alkyd metals? Like see this one, UF, this one is, yeah, UF4. UF4 has to undergo a reduction reaction. So UF4 plus 2 calciums will give uranium metal, pure uranium metal, plus this one is Ca2, okay, 2 CaF2. Okay, 2CaF2. So this is uranium metal, pure uranium metal, and this is calcium fluoride, FluORide. Or whenever your alkali metal you chosen as a magnesium, then it will be UF4 plus 2 magnesium will gives rise to same uranium uranium metal, then 2 MgF2. So that is magnesium fluoride. Okay, further your this one, yeah, fluorination. Further, this product can be fluorinated. This UF, from the reduction you are getting U. Then this further the uranium tetrafluoride can also be converted to uranium hexafluoride UF6. So how to convert that one? That will be converted using fluorination. FLUORINATAO. Yeah, fluorination. So how to do the fluorination? We have to supply some fluorine gas to the this one UF4 uranium tetrafluoride. So this will be fluorination. So what is the fluorination reaction? Fluorination reaction is nothing but UF4 plus you have to add F2. Then you will be getting UF6. So uranium, this is called hexa. 6 means hexa fluoride. So first one is according to the flow sheet. So first you will be having uranyl nitrate hexahydrate. So this is one form of your uranium. This form of uranium will be looking in a yellowish color. So that yellowish color uranium has to be transformed into UO3, uranium trioxide. So to do that one, it has to undergo denitration process. So the denitration process will be happening using this reaction. Uranyl nitrate hexahydrate will be converted to uranyl nitrate along with the liberation of 5 molecules of hydrogen and 1 molecule of your nitric acid. So that is, this nitric acid is nothing but this liberated NO plus NO2. Then this uranyl nitrate will undergo further a nitration process along with liberation of one nitric acid with the liberation of UO3, uranium trioxide. Then this uranium trioxide has to undergo a reduction reaction to form a uranium dioxide. So reduction reaction, we know that one. Reduction means removal of oxygen. So to remove that one, we have to add hydrogen to that particular UO3. Then UO3 will be coming as a UO2, which is uranium dioxide, along with liberation of half molecule of O2. Then this UO2, uranium dioxide, can be converted to uranium tetrafluoride. How to convert that one? UO2 has to be mixed with hydrogen fluoride or hydrofluoric acid. After mixing this one, this reaction will be going. Then uranium tetrafluoride will be formed along with the liberation of two molecules of water. Then further this UO2 can be converted to uranium carbide UC2. So we have to send this uranium dioxide to the carbide furnacing with carbon as the one of the material. Then UO2 will be reacted with this carbon, 4 carbon molecules, and it will be liberating you uranium carbide along with the liberation of carbon monoxide. Then after that, this uranium fluoride will be further converted to pure metal uranium by just, okay, here the product is UF6. Okay, this uranium tetrafluoride will be converted to further the pure uranium metal using reduction using alkali metals such as calcium or magnesium. So then UF4 will be reacted with calcium or magnesium. So two parts of calcium, then it will be giving a pure metal uranium plus two molecules of calcium fluoride, which is CaF2. If your chosen alkali metal is a magnesium, so this reaction will take place and it will be forming pure uranium metal and magnesium fluoride, two molecules of magnesium fluoride. Then further, if you want to convert this uranium tetrafluoride to your uranium hexafluoride, you have to enrich with, you have to fluorinate that particular UF4 with fluorine. So UF4 plus F2 will be reacting to form a uranium hexafluoride. So all this, there are many products. So first product from this raw material uranium nitrate hexahydrate is, first product is UO3, and next product is UO2, and next product is UF4. Then next product is UC2. Then next product is pure metal uranium, and the final product is UF6. All these products are possible from only one mineral, that is uranyl nitrate hexahydrate. Okay, that is given clearly in the flow sheet, that one. Okay, first the uranyl nitrate, you will be looking like this. Okay, yellowish material. From this material, it has to go denitration process, then it will be giving UO3. Then this UO3 has to undergo a reduction process to give UO2. Then after this, this UO2 has to undergo a hydrofluorination to give UF4. Then this UO2 has to undergo a carbide furnacing to give uranium carbide UXCY, that is nothing but UC2. So uranium carbide, that one. Then further this UF4 has to undergo a reduction using alkali to give pure metal uranium metal. Then further this uranium tetrafluoride has to undergo a fluorination process to give uranium hexafluoride. So this is overall flow sheet, and apart from that one, you can explain using these reactions. So in the textbook, these reactions are not there, only the flow sheet is there. So you have to, in the exam, it will be good if you write these reactions. So remembering is very easy. Okay. Any doubts until here? Any doubt or blank? What? I have to continue, I have to stop, or what? Don't understand.
No doubts, sir.
Okay, thank you. Then next and last topic of this part A of unit 1 is role of chemical engineering in nuclear engineering. So all this, whatever we have discussed now, denitration, reduction, hydrofluorination, carbide furnacing, reduction, fluorination, or whatever the nuclear fuel cycle, all this, whatever we have discussed, where is the part of chemical engineering here? So what the chemical engineering candidate will do in this nuclear engineering? What is his role? So to discuss that one, there are many certain points are there. This is also one important question. Explain the role of chemical engineering is nuclear engineering. They are asking many times this question. So where do we involve there? So there is a reactor. Okay, reactor design will be the unique characteristics of chemical engineer. Only chemical engineer can design the reactor on a large scale. He has to do that one. So the chemical engineering has to play a major role in the nuclear engineering in such a way that he has to design and operate the fission reactor, which are useful in nuclear fuel cycle. So operation of these reactors needs a chemical engineer. Not only operation, but designing of this reactor also looking after by the chemical engineer. Then next one is a nuclear raw materials separation and preparation of nuclear fuels. So nuclear fuel is not directly the fission fuel, or if there is a fission fuel also, it has to enrich, it has to concentrate, it has to purify. So separation and purification preparation of nuclear fuels will also be looked by the chemical engineer only. So here if you see the ore mining, this will be looking by the mining people. Extraction, concentration, enrichment, all these operations will be designed and operated by the only chemical engineers only. There is a role of chemical engineer in this section also, not only in the reactor design and operation, but also in the purification and separation of the raw material also. The role of chemical engineer is there. The next one is nuclear fuels burning and heat removal. So in the burning, okay, how the nuclear fuel has to burn inside, what type of coolant we have to use, okay, how the jacket needs to be there, how the coolants or moderator has to enter into the reactor. So all things will be looked by the chemical engineers, and at the same time how much heat has to extract from that particular reactor, how much coolant has to supply inside that reactor, everything will be looked by the only chemical engineers only. Okay, in the nuclear fuel burning as well as heat removal also chemical engineering is involved. And spent fuel reprocessing, okay, after spent fuel, okay, fuel has been spent, whatever the byproducts, whatever the off products, whatever the radioactive metals, whatever the waste has been formed, in every process the chemical engineer has to play a major role in spent fuel reprocessing, and also utilization of fission products like isotopes of iodine, cesium, strontium, xenon, barium. In processing all those products also chemical engineer has to play a major role. And at the same time in the disposal of radioactive waste, okay, in the disposal of this radioactive waste, and also in the off products, okay, like a useful products, fission products separation, okay, use this products utilization, everywhere the chemical engineer has to play a major role. That is the role of chemical engineer in the nuclear engineering. Nuclear engineering means not a separate field, that is, so some candidates with a mechanical background, some candidate with a electrical background, some candidates with a chemical background, okay, some candidates with some other engineering background will be just learning some of the basics of the nuclear engineering, and they will be called as a nuclear engineers. So that is the part, but there is no as such a nuclear engineering purely. So they has to borrow some of the subjects from every branch of engineering. So chemical engineering has to play a very major role in the nuclear engineering, right from designing of a reactor, okay, separation of a raw materials, fuel processing, heat removal, spent fuel processing, utilization of a off products or fission products, then disposal of waste. From the start of the raw materials to the final product production, everywhere there is a role of a chemical engineer. So this is also a very important question. You have to read in the notebook. It has been given clearly. Okay, any doubts until here? The part A. This is the completion of part A. From the next class, we will be starting the part B. Okay, everybody in sleeping mode, I guess. Okay, not part B. Okay, this is not a last part of your part, last part of part A. So one more topic is there in part A, which is heavy water or deuterium oxide production. So what is heavy water? How to produce the heavy water? What are the application of heavy water? We can use as a coolant. We can use as a moderator in the nuclear power plant. So how to produce that heavy water? What are the sources? What are the raw materials required for this one? What is the plant design? Everything we will try to learn in the next class. Okay, this is the last topic of your part A. After this heavy water production, we will be going directly to the Part B, this is explosives and propellants. Okay, if nobody is sleeping, then please respond. If you have any doubts, you can ask me. Otherwise, no doubt, something you have to respond me. Otherwise, I couldn't understand. I'm clueless.
No doubt, sir.
Okay, then.
Mm.
Okay, then if you have any doubts, you can utilize this couple of minutes, or otherwise we will conclude. Okay, only one person is responding. Apart from that, nobody is responding.